40-flow MRI gives a comprehensive assessment of aortic hemodynamics by acquiring time result through directional blood flow. It is able to provide a 3D visualization of blood and extensive analytics for the characterization of hemodynamic changes. However, the evaluation of flow dynamics from 40-flow MRI requires manual and cumbersome data analysis, including the 3D segmentation of the thoracic aorta, limiting clinical translation and increasing inter-observer variation. Previous efforts at automated methods attempted to derive generalizable landmark features from small and homogeneous patient cohorts. However, translation of such features to larger cohorts with heterogeneous patient population can be challenging due to the high variability in aortic shape, size, and geometry. Using the recent developments in deep learning and convolutional neural networks, we sought to develop and evaluate a deep learning-based method that enables fully automated 3D aortic segmentation from 40-flow MRI for fast and reproducible evaluations of aortic dimensions and flow using a large data set spanning a wider range of ages and aortic diseases, sizes, and shapes. For this study, we used 1,018 subjects across a wide age range who underwent 40-flow MRI, including 528 bicuspid aortic valve patients, 376 tricuspid aortic valve patients with dilated aortas, and 114 controls. The scan parameters are shown here. Data for all subjects were acquired during free breathing with respiratory navigator gating, and using either prospective or retrospective ECG gating. 499 data sets were used for training, 101 for validation, and 418 for testing. All subjects were analyzed using a standard 40-flow pre-processing pipeline. Pre-processed data was used to calculate a 3D phase contrast angiogram, which served as the basis for manual 3D segmentations, as well as serving as an input for CNN. This manual PCMRA-based 3D segmentation was used as the ground truth for training, validation, and testing. The convolutional neural network used, as described previously, is a 3D UNet network with dense-net blocks replacing the original convolution layers. The dense-net blocks featured a constant convolution channel size of 12, reducing the overall number of parameters and mitigating overfitting by controlling the growth of the feature maps across the network. Additionally, the dense-net blocks concatenated all prior feature maps for use as inputs for subsequent layers, ensuring efficient feature reuse, as shown in Part B of the figure. As you can see in Part A, the encoder section used max pooling for downsampling layers, while the decoder section used transposed convolution for upsampling. The final layer consisted of a 1 by 1 by 1 convolution and softmax function to generate a probability of each voxel in the input for the binary classes. A composite loss function featuring a softmax cross entropy plus dice loss was used during training. To assess the performance of the CNN, dice scores, Hausdorff distance, and average symmetrical surface distance were calculated between automated and manual segmentations. For flow quantifications, 3 2D analysis planes were manually placed at the ascending, arch, and descending aorta. Maximum velocity was calculated as the 95th percentile of velocity values at peak systole, and flow time curves were used to determine peak and net flow for each of the 3 planes as seen in the example here. In addition, the maximum lumen diameter was extracted by fitting an ellipses at the cross-section and taking the major axis for each of the 3 planes. Inter-observer comparisons were performed on 40 randomly selected datasets by 2 observers of 2 years' experience. In order to examine the most common discrepancies in our study, all CNN segmentations with dice scores less than 0.9 were manually assessed for notable differences compared with their corresponding manual segmentations. Segmentation performance metrics were reported as the mean plus or minus standard deviation for normally distributed data, or the median and interquartile range for non-parametric data. Flow metrics and lumen diameters were compared with their corresponding manual generated segment values by Bland-Altman analysis. Linear regressions were used to assess the impact of demographic and scan parameters on CNN performance with dice scores as the metric, and comparisons were performed to assess the performance of the CNN on different MRI field strength, as well as for different sex in the presence of contrast agent using an unpaired t-test or a Mann-Whitney U-test. For the results, the CNN demonstrated excellent performance for the testing cohort, with a median die score of 0.951, a Hausdorff distance of, a median Hausdorff distance of 2.8, and a median average symmetrical surface distance of 0.176. 3 examples are shown here, with the manual segmentation in red and the automated in blue, featuring subjects with an excellent die score of 0.96, intermediate die score of 0.89, and the lowest die score found for the entire testing cohort of 0.77. Additionally, we saw the CNN was stable with age, VANC, heart rate, and BMI across the testing cohort, and no significant differences were found in die scores between different MRI field strength or sex. However, the CNN was sensitive to voxel size, with a small decrease in die scores with increasing voxel sizes, and a significant difference was found in die scores between contrast and non-contrast scans. The aortic diameter comparisons are summarized below, with Bland-Altman analysis for the testing cohort showing a low bias between -0.2 to 0.001 millimeters, and excellent limits of agreement between plus or minus 1.9 to plus or minus 2.4 millimeters. For flow comparisons, 4 BAV subjects with severe ileusing were excluded, resulting in a total of 414 subjects for this analysis. Net flow was found to have a low bias between -0.2 to 0.1 milliliters per cycle, and strong limits of agreement between plus or minus 3.5 to plus or minus 5.3 milliliters per cycle. Additional comparisons were performed for peak velocity and peak flow, showing excellent agreement with the limit of agreement percent difference, less than 10% of the mean manually generated reference values. For categorizing the most common discrepancies between the CNN and the manual segmentations, 34 datasets were found to have a die score below 0.9. The table summarizes our findings, with some datasets being included in multiple categories. The most common discrepancy found were differences in aortic root segmentations, with the CNN more likely to include the aortic root and the outflow tract in the segmentation compared to the manual user. And finally, the CNN showed excellent agreement with our expert observers. Across all metrics, our CNN performs as well or better to our observers compared to our inter-observer comparisons, as seen in the table. Additionally, the CNN was able to perform segmentations at a fraction of the time, taking less than 1 second to perform one segmentation compared to 10 minutes manually. By providing rapid and accurate aortic flow and diameter metrics, our CNN was able to improve the repeatability and clinical feasibility of 4D flow MRI. Future direction of this study is to validate our current CNN to generate time-resolved aortic segmentations for oscillatory shear index calculations, as well as to further develop CNNs for other vasculature, like the pulmonary arteries, for QP-QS calculations. Additionally, we hope to expand the generalizability of our model across multiple vendors and centers through a multi-center study. Finally, I'd like to thank and acknowledge all of my collaborators. Thank you.